The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Okay, so remember last time on Tuesday we learned about the chain rule. And so, for example, we saw that if we have a function that depends on three variables x, y, z, but x, y, z themselves depend on some variable t, then you can find a formula for dw dt by writing down w sub x dx dt plus w sub y dy dt plus w sub z dz dt. And the meaning of that formula is that, well, the change in w is caused by changes in x, y, and z. X, y, and z change at rates dx dt, dy dt, dz dt, and this causes the function to change accordingly using the partial, in terms of the partial derivatives tell you how sensitive w is to changes in each variable. Okay, so we're going to just rewrite this in a new notation. So I'm going to rewrite this in a more concise form as gradient of w dot product with the velocity vector dr dt, where so the gradient of w is a vector formed by putting together all of the partial derivatives. Okay, so it's the vector whose components are the partials. And of course, it's a vector that depends on x, y, and z, right? These guys depend on x, y, z, so it's actually one vector for each point x, y, z. You can talk about the gradient of w at some point x, y, z. So at each point it gives you a vector. That actually is what we will call later a vector field. But we'll get back to that later. And dr dt is just the velocity vector dx dt, dy dt, dz dt. Okay, so the new definition for today is the definition of a gradient vector. And our goal will be to understand a bit better what does this vector mean, what does it measure, and what can we do with it. But you see that in terms of information content, it's really the same information that's already in the partial derivatives or in the differential. So, yes, and I should say, of course, you can also use the gradient in other things like approximation formulas and so on. It's just, so far it's just notation. It's a way to rewrite things. But, so here's the first cool property of the gradient. So, I claim that the gradient vector is perpendicular to the level surface corresponding to setting the function w equal to a constant. Okay, so if I draw a contour plot of my function, so I'm going to actually forget about z because I want to draw a two-variable contour plot. So say I have a function of two variables, x and y, then maybe it has some contour plot. And I'm saying if I take the gradient of a function at this point, x, y, so I will have a vector. Well, if I draw that vector on top of a contour plot, it's going to end up being perpendicular to the level curve at this point. Same thing if I have a function of three variables. then I can try to draw its contour plot. Of course, I can't really do it because the contour plot would be, living in space with x, y, and z. But it would be a bunch of level surfaces, and the gradient vector would be a vector in space. That vector is perpendicular to the level surfaces. So let's try to see that on a couple of examples. So let's do a first example. Let's do things, what's the easiest case? Let's take a linear function of x, y, and z. So I will take w equals a1 times x plus a2 times y plus a3 times z. Well, so what's the gradient of this function? Well, the first component will be a1, that's partial w partial x. Then a2, that's partial w partial y, and a3, partial w partial z. Okay? Now, what are the level surfaces? Well, if I set w equal to some constant c, that means I look at the points where a1x plus a2y plus a3z equals c. What kind of surface is that? It's a plane, and we know how to find a normal vector to this plane just by looking at the coefficients. So it's a plane with normal vector, exactly this gradient. And in fact, in a way, this is the only case you need to check because of linear approximation. If you replace a function by its linear approximation, that means you will replace the level surfaces by their tangent planes. And then you will actually end up in this situation. But maybe that's not very convincing. So let's do another example. So let's do a second example. Let's say we look at the function x squared plus y squared. Okay, so now it's a function of just two variables, because that way I will be able to actually draw a picture for you. Okay, so what are the level sets of this function? Well, they're going to be circles, right? W equals c is a circle. X squared plus y squared equals c. So I should say the level curve is a circle. So the contour plot looks something like that.